All right, then just the final technique, when you're dealing with electrons, it's not enough to just say, is there an electron or not? Or for us, the atoms that mimic these electrons, the two spin states, for the atoms that mimic the two electronic spin states in the material, we really want to know, is there a spin up on a side, a spin down on a side? Are there spin up and downs on a side, or an empty side? So we have 4 configurations that we have to deal with, that we want to detect. And the way we do this is we start with a physical system. Let's say this is this 2D system with the given lattice structure that you want. And then for detection, just for detection, we actually basically separate the spin ups from the spin down into 2 layers. We call this the spin splitting, like a Stern-Gerlach experiment. And then you just image the 2 layers, one occupied by the spin ups and one by the spin downs. But remember, they were together in the physical system here in this monolayer. So you can put this together, this information, and then completely reconstruct the occupation of your lattices, where the spin ups were, the spin downs were, the doublons, the doubly occupied sites, or the holes were in the system. And so if you think about what we're really doing here, is we're taking, a many-body wave function. We're creating an interesting many-body state in these lattices. And once we take the photo, once we do the detection event, we project, let's say, this complex superposition state that we have onto one spatial configuration that we're actually seeing in the experiment then. And this would be, let's say, a photo that you see in a single snapshot. Maybe the wave function collapses onto this configuration, then this will be the configuration you see in the experiment in this particular run of the experiment. So now that's destructive. Then you have to recreate psi again, and then do another measurement. Maybe then you see another configuration. And you do this thousands of times in your experiment. And then in the end of the day, what you get is a probability distribution of configuration. So you know how likely was it to have this configuration, that configuration, or the other configuration. And from these probabilities of configurations, I'll show you, we can then calculate correlation functions that tell us something about the interesting physics that's going on in the system. At the end of the talk, I'll also tell you about, you might wonder, why is he not writing out the complex coefficients here, the C coefficients? Don't they play a role too? That's of course true. And right now, if you just do a population measurement, you're only measuring the norm C squared, so the probabilities of being in that configuration. We would also like to know about the phases, and that's something we can do when we measure, for example, currents in the system. And I'll come back to that maybe at the end of my talk, where I'll give you an outlook how that also works. All right. So
Immanuel, yeah. I think you very well anticipated one of the questions, which is exactly about the phases. So
sure.
Back to that. The other question was, you had this doublon on your slide. Maybe if you just tell us a little bit about that.
What that is? So the doublon just means you remember in electrons, think of electrons, you have a spin up electron and a spin down electron, and on a lattice. And so if you have 2 spin up and a spin down on a lattice side, that's what we call a doublon. So you can put, by Pauli principle, you cannot put 2 spin ups on one side. That's blocked by Pauli principle. But you can put on a single lattice side in a material, you can put a spin up and a spin down particle.
Right. So in this case, that's a feature, not because in the pictures on the left, it kind of looks like the lattice in the image has morphed and deformed a little bit, so that this is in this case a desired feature, not a artifact.
Yeah, so the doublons are not an artifact. They occur in the system. They are part of the physics, and we want to detect them, right?
Thank you.
Very good. Okay. So here's some more pictures of how these look. For example, when we are dealing with so-called Mott insulators, so these are strongly interacting, in this case bosons or fermions would look the same, where they basically sort themselves out to, let's say, single atoms per site. So these are not arrays that have been sorted by us. So just nature does it for us. The physics of the strongly interacting repulsive particles does not want to have 2 particles sitting together, and then they basically separate from each other. And you can see very nicely they do this in a rather homogeneous way. There are some defects. These defects could be part of the physics that you're studying, so it could be quantum fluctuations in the system that generate this, or they could be finite temperature effects, of the phase you have. There could be finite temperature defects that you have in that system. And typically, this is a picture, we're dealing with systems of up to 2,000 to 5,000 atoms that we can study in this way. All right, so let me turn to one physics problem that I think is the reference problem for material science. You know, we in our quantum computer simulators, we always say we want to study material physics, material science, and I think the reference problem in that context is the so-called Fermi-Hubbard model, where you basically just have electrons, spin up-down electrons on a lattice. The electrons can tunnel from one side to the next, and then when they come together on one side, a spin up and a down electron, they can interact, and they interact very strongly and give rise to this repulsion U. So this can be expressed in this Hamiltonian. The first one just describes the tunnel coupling. The second term describes the interaction part of your system. And that's what you want to study. And, you know, we're also interested in this simple Hamiltonian because even, 40, 50 years after its introduction, we're still not entirely sure what the phase diagram of this Hamiltonian is, but we believe there are some deep connections to high TC superconductivity here. Now, there's a special case when you have exactly 50% spin ups and spin downs in this model, and you have strong repulsion. Then this Fermi-Hubbard model maps onto actually a Heisenberg Hamiltonian. So you get a spin Hamiltonian with antiferromagnetic spin couplings. So the system will want to order antiferromagnetically. And then if we go to the real materials, if we take a look, on a phase diagram of these high TC compounds, you typically find this interesting zoo of phases, which people are trying to make sense of, where you have the undoped situation here to the left, and that's the situation I just described. There you find antiferromagnetic order in the system, and as soon as you start to dope the system, you start to see that all these zoo of phases break loose. There's this D-wave superconducting phase here. There's this very mysterious pseudo-gap phase here that people are really puzzled by what this is. And if you want to express, what is the simple question we're trying to answer here, what is the physics we're trying to study, it's basically how do holes, simple dopants, when you take out an electron, you inject basically a hole into the system, how do holes that move around in this antiferromagnetic environment, how do they compete with this tendency of the system to form antiferromagnetic order? So that's, from a physics point of view, the difficult question that you want to answer. Well, the question sounds simple, but turns out it's actually very, very intricate and difficult. And there, of course, it's nice that if we can build such an artificial model system in our quantum simulation approach, then we can just directly look into the system and really take photos and see what each of the individual electrons is doing. So here I'm actually showing you a picture of how this looks in the experiment. So we have a physics region, a flat region where we do the physics, where the lattice is. We have a reservoir connected to that, which we just use for cooling. And then we take those images that I showed you before, and then I can, for example, measure the average density of my particles in the system. If I can look also at the fluctuation, the particle number fluctuations on a site, or I can look at if I do the spin resolved detection, I can measure spin-spin correlations in the system. So I can measure how is the Z component on the spin on this side correlated with the Z component of the spin on that side. And you can see, for the temperatures we reach, we can really see this very beautiful antiferromagnetic order appear in the system. So we are at low enough temperatures where the system has antiferromagnetically ordered over large parts of the system, over a few hundred lattice sites in the system. And just to check how good is the simulator we can check against numerical methods. And so we can turn to people like Lode Polle here in Munich, who are experts on quantum Monte Carlo simulations, and we can compare this spin-spin correlation function to numerics, which is this line here, which agrees perfectly with what we measure. So in this regime, in this undoped regime, quantum Monte Carlo works perfectly, and it serves as a good reference point. But as soon as we start to dope the system, quantum Monte Carlo, for example, will break down to work efficiently anymore, and we can really go to the full advantage of the approach. So let me show you the physics, what happens when you put a hole into this antiferromagnet. And so imagine you have this antiferromagnetically ordered system and you put a single hole in here, and holes in quantum mechanics never want to stay in place. So in order for them to minimize their kinetic energy, they always want to move, they want to delocalize. But if they move around, and you can see that immediately, if this hole moves to this side, the green atom, the spin down, maybe has to move here. So this configuration emerges. And if then the hole moves another side, then actually the red atom has to move in here. And you see that the more the hole moves, the more like flip string of spins it leaves behind, but these string of spins are now ferromagnetically aligned parallel to each other, but that's not favored by the model. The model, remember, wants antiferromagnetic ordering, but when the hole moves, it creates this energy penalty. It destroys this antiferromagnetic order and leaves a strong energy penalty behind, which means basically that this hole cannot move indefinitely because of this flipped strings of spins it leaves behind. And the more it moves, actually, the bigger the energy cost becomes. This energy cost increases linear with movement of the hole. And you can think of these flipped spins and the hole as basically being connected by a string, and the energy of this string grows linearly with separation of these spins, these flipped spins, and the hole that you have. And that's actually very similar what we know in physics, that what occurs in nuclear physics. That's exactly the effect of confinement that gives rise to mesons, for example, in high energy physics, our elementary particles. So we expect the same thing to happen here, a new elementary particle to occur in our electron cloud. And indeed, what happens here is indeed a new quasi-particle forming, and this is what we call the magnetic polaron, which is basically this hole surrounded by a distorted cloud of spin correlations, which arises due to the motion of this hole in this antiferromagnet. So that's the new particle, and whenever this hole moves, it always has to drag around with it this spin flipped cloud together, moving with it, and that's what we call the magnetic polaron in the system. So here I show you some very nice data, some very recent data, that one wants to calculate. You could want to do that on an IBM quantum computer. We do it on our quantum simulator. This is how the spin environment around this hole actually looks like. So let me show you what I'm plotting here. So let's say we center a hole here on this side, or a doublon, it doesn't matter for this experiment we're doing. And we're asking how are the spins changed compared to the background when you find a hole here. So we can plot the spin-spin correlator, which is indicated by this ellipse here, and ask how is this spin-spin correlator modified depending on finding a hole here in the center of the system. So your reference frame is now this moving hole. You always focus on the hole, and you ask how are the spin correlations modified. And here's the so-called connected correlation function that we measured in the quantum simulator that gives us a very quantitative prediction of this dressing cloud, of this flipped string of spins that surround this atom moving around in the system. So that's a very nice result that you can really now try to compare to numerical methods. It's very hard actually to calculate. And there's actually a very recent nice experiment also from my colleagues in Harvard and Princeton. I just showed results here from Princeton, from Wasim Bakker's group, how this works on a triangular lattice. There's a different kind of physics at hand. Frustration is at hand, and kinetic induced polarons form. But again, you can also see the distortion of the spin cloud surrounding this impurity moving around in the lattice. To the question, Zlatko?
Yes, maybe a quick question from Bektor, and I'm not sure, maybe you have this somewhere on your slides, but there was a question of what the correlation decay rate was like, if it was a power law or an exponential.
Yeah, that's a very good question. So it's not. So I think for our case, we can't. It's not so clear. We have to analyze this data. This is brand new data, so we didn't analyze for that. So it's a very interesting question. So the size of this polaron depends on the basically on the ratio of kinetic energy of the dopant relative to the magnetic exchange energy of your electrons in the system. And that should scale, like the size of this polaron cloud, this dressing cloud, should depend strongly on that, and that will be something very interesting to look at. And remember, what I'm showing here, indeed, that's very important, is a quantity that you cannot measure in condensed matter physics. So condensed matter physicists in the experiment can only measure 2-point correlation functions. And that would not allow you to show this. So this is really a big advantage of our quantum systems that we have at hand, that we can analyze this. Why do we want to know this? What this 3-point correlator tells me, it tells me how are these spins on side r plus I and r plus j correlated, conditioned on having a hole at site r. And that's precisely what I'm plotting here. So there's a hole on site r, and I'm asking then how are these spins correlated, but I'm always conditioning it on having a hole in the center. So we're really looking at how the spins are distorted around this hole around this mobile dopant that's in the system. So that's very important. So it's really a unique correlator, 3-point correlator that really highlights the features or directly allows us to visualize this polaron cloud.